So this is Fun with Electronics Project 2, Part 2A. So this is a three-stage astable multi-vibrator or astable oscillator, whatever you want to call it. So in each stage, each time constant is different. So troubleshooting was very painful. And these were the values that I came up with after trial and error, after so much plug and play. So you can see for the first stage, I'm using a 3.3 microfarads and a 10k ohm resistor. And for the second stage, which I like to call it the blue stage, I'm using again a 3.3 microfarad, and this time I'm using a 5k ohm resistor. For the third stage, which I like to call it the green stage, uses a 22 microfarad capacitor and a 22.5 kilo ohm resistor. And here are the time constants, which are different, which is what we want to see. Different LED oscillating at different time constants, which is what I'm getting right now. As you can see, each LED is oscillating at a different time constant. And here is a waveform. The oscilloscope I'm using is a NERC 2C5 3T 3-in-1 oscilloscope, which provides what a normal oscilloscope provides, but not with the extended features a normal lab oscilloscope would provide. But it's enough to show the details and the behavior of a circuit, which in this case is an astable oscillator. So as you can see, the yellow waveform is channel 1, which is the red LED, which is connected to the cathode, I believe, of the LED. And the blue waveform is channel 2, which is hooked up to the cathode, to the positive side of the LED, which is basically right over here for channel 1 and right here for channel 2. Yep. And in those empty spaces between the blue waveform and the yellow waveform represent the charging time of the green LED, which is the green stage. Yeah, pretty cool. And to show proof that the empty spaces represent the charging time of the green LED, I hooked up channel 2 to the cathode of the green LED, which is a positive side, I believe. Hooked it up to the second waveform, which is the blue waveform, and as you can see, it's the charging time is basically the same duration as the empty spaces demonstrated previously. So yeah, pretty cool. All right, so for part 2 AI, we're going to implement an LDR, also known as a photoresistor, between the bases of the blue stage and the green stage. So pretty much in those 2 points, and which is already done in hardware. So we have the LDR right over here, and right now it's at its normal dark condition state. And when I shine the LDR with my phone's flashlight, the oscillation went at a faster rate. Yeah, when I turn it off, it goes back to its original state. I mean, right now it's original because the room where I'm at, it's pretty dark. So I turn the flashlight again, and the LEDs are oscillating quicker. Turn it off. Slows down. Cool. All right. So now let's see the difference using the oscilloscope. So I have channel 1 connected to the red stage, to the anode of the red LED, and channel 2 connected to the anode of the blue LED. So right now, as you can see, it's at its dark condition state. And now when I shine the LDR, as you can see, the charging time, like the space, the the space in between decreased a bit. The charging time decreased. So now um when I face my light away, as you can see, the charging time, sorry, increased a bit. I shine the light again, and then it decreases. The charging time decreases and just oscillates faster. See, there you go. It may not look much, but if you take a look at it real closely, you might be able to see it. The gap, the charging gap that that you can see gets wider, and then when I shine the light, the gap decreases. The charging gap. Okay, so for part 2A double I, we're implementing a fixed resistor in series with the LDR, basically in the same area, in between the bases of both the blue stage and the green stage, which I like to call them. And just for fun, we'll see what happens when we implement different resistor values. So we'll see what happens when an LDR is in series with a 220 ohm resistor, when it's in series with the 4.6 kilo ohm resistor, when it's in series with the 100 kilo ohm resistor, and an 851 kilo ohm resistor. And we're gonna start with the 220 ohm resistor. So there's a circuit for it. So you could barely see it. Sorry for that. Sorry about that. This is the resistor right here. It's in series. Yeah, it's in series with the LDR. And right now it's in its dark condition state. And when I shine my lamp on the LDR, as you can see, the oscillation gets faster, which can be seen here in the oscilloscope. Basically, what happened the previous circuit. Dark condition, light condition. The oscilloscope setup is pretty much the same as the previous circuit. The channel 1 is connected to the anode of the red LED, and channel 2, which is the blue waveform, is connected to the anode of the blue LED. So in hindsight, I realized I've said cathode, but actually it's it's the anode, which is the positive side. So sorry for that. Sorry about that. All right. Dark condition, light condition, and the empty gaps, as you can see, represents the green LED oscillating. Yeah. All right. Now we're switching the fixed resistor from 220 to 4.6 kiloohms, which was already done. And now let's see what happens. All right, I shine the light. Looks like the oscillation changed a little bit. Not so sure. Let's take a look at the oscilloscope. All right, here the dark condition. This is the dark condition right now. Light condition. Some minor changes in the charging time. I believe it decreased a bit. The charging time went up. Sorry, the charging time. I guess it went a bit down. Dark condition. Okay, I think it's I think it's visible. Yeah, it's visible when you actually look at it. So the same result as in the previous circuit. All right. All right. Now we're trying it with 100K resistor. All right. I got it plugged in. Now let's see. I'm guessing it's slowing down a bit. Could be wrong. Let's take a look at the oscilloscope, see what it says. Sorry about the glare. I'm doing this from home. Light condition, dark condition. So there, right now I see no changes. Now last but not least, 851 kiloohms. That's the circuit. Right now it's in its dark condition state. Shine the LED, see what happens. Okay. Looks like it's slowing down. Yes. It slows down in its light condition state. Looks like it's oscillating much slower. Now let's see what the oscilloscope says. Okay, right now it's in its dark condition state. Now when I shine the light, looks like the duration is increasing. Let's see it again. I believe it's a small change, but nothing significant. But just by looking at the LEDs, it looks like the oscillation slowed down when the LDR is shined by the light, which in this case is my lamp, which is my desk light. As you can see, which is the same for the previous cases, for the previous circuits. Yeah. So, in conclusion, as the fixed resistance between the bases increases, the difference in oscillation between light condition and dark condition decreases. The resistance increases, and the difference in oscillation speed decreases.